All right, good afternoon. So this is the first of two talks that we have. Dan is going to follow up with talk about the FAST and the investigation team. But I'm going to be talking about the ARM mission and just give you an overview of what to expect. So we have three main segments to the Asteroid redirect mission. We have an identify, a redirect, and explore. So for the identify segment, we're using our ground-based and space-based assets to not only find targets, but also to characterize them and have them selected. So we have the search telescopes such as Pan-STARRS, and also using NEOWISE, and we have our planetary radars, which are Goldstone and Arecibo, and then some characterization assets such as the infrared telescope facility. For the redirect portion, we're using solar electric propulsion to actually go to the main asteroid and pluck a boulder off the surface and return it to cislunar space. And then for the explore segment, we have the crew launching on the SLS, riding in Orion, and, excuse me, going to rendezvous with the robotic vehicle, and then actually performing some spacewalks and exploring and investigating the boulder. So in terms of the contributions to deep space human exploration, there are four main things that ARM actually does for us. We want to try and demonstrate advanced autonomous proximity operations in deep space. It's something we need to do. We also want to try and develop our high-power solar electric propulsion to transport heavy cargo around. This is we're going to be doing this with a boulder, but that's going to be similar to analogous to what we do with a habitation module or a resupply module. And then we also want to demonstrate that we can perform integrated crew and robotic operations in deep space. And then also really important is for the human exploration is to conduct EVAs, extra vehicle activities, in deep space for interacting at natural bodies, performing investigations, taking samples, properly containing those samples, and then bringing those back to Earth. So we have a couple of technologies that we're trying to develop, and this is part of the pole proving ground in cislunar space. So we're developing the high efficiency large solar electric arrays. We're going to be, again, doing some work on our EVA capabilities and some of the protocols that we're going to be doing related to exploring the boulder. Developing our high-power solar electric propulsion. We have a provider that is going to provide some of the engines for the vehicle, for the big robotic vehicle, and then developing the sensors and capabilities that are needed for our rendezvous and docking operations. So this is the alignment strategy for the ARM mission. So we have the identification segment, as you can see in the timeline. We used various assets. And our final target selection will not be made until December 2020. We have a reference target. I'll talk about the targets that we have for reference and the target suite that we have as backup. But we won't make our final target selection for sure until December 2020. We are still keeping the options open, although we do have right now a pretty good reference target. For the robotic vehicle, we're looking at a launch of December 2021. Based on the asteroid that we have selected, we'll probably be able to rendezvous with it in the 2023 timeframe, conduct operations, perform a planetary defense demonstration, and then later in the 2025-2026 timeframe, actually conduct a mission back to the cislunar space for there, and then it will be there available for the crew operations for rendezvous. You can see down for the crewed mission, the ARCM mission, we're going to be coming in after EM2. And again, we're looking at a time frame for the crew launch somewhere in the late 2025, 2026 time frame for actually launching a crew out to the robotic vehicle. So this is just a sort of a bat chart of the actual overview of the asteroid redirect mission. Basically, our launch vehicles that we're looking at right now has not been selected, but we're looking at a Delta IV Heavy, maybe a Falcon Heavy, or the Space Launch System, SLS. We have a period of checkouts, deployments, We have an outbound cruise. We have some asteroid operations. I'll go into these in more detail, but looking at an asteroid operations of about 230 days. And then have an inbound cruise phase, and then transfer to an orbit where the crewed mission can actually rendezvous with the vehicle, conduct crewed operations, and then we're going to transfer the robotic vehicle with the Boulder into a long-term stable orbit. And this orbit will be stable for hundreds of years. So here are our current candidate parent asteroids. Some of these are going to be very familiar for most of you. We have Itokawa, which was the target of the original Hayabusa spacecraft. We have Bennu, which is the target of the OSIRIS-REx mission, which is going to launch this September. And we have 1999 JE3, which is the Hayabusa 2 target, which is already in flight and actually doing very well. Our reference target is 2008 EV5. This was the target of the Marco Polo R mission that ESA unfortunately did not select for one of their M-class missions. That was a sample return mission. But 2008 EV5 is a bona fide target of scientific interest. It's a carbonaceous target. It's of interest for ISRU purposes as well. It's also one of the targets that is of interest for actually sending people to a near-Earth asteroid, because it is one of the largest asteroids that has the lowest delta V. So again, this is our reference target. This is what we're working towards currently, and we'll see how we go. So here's our proximity operations overview. We have several phases of this. The first 15 days is an approach where we look at the target, make sure there's no hazards and nothing, no small moonlets or anything like that. Then we have a characterization phase of about 85 days where we can actually understand the gravity field, understand the surface, look for areas of interest in terms of boulders that we may be able to collect. And then we have a boulder collection segment of about 50 days with a 50-day margin, so that we have 50 days allocated for actually collecting and selecting the boulder. We have a 50-day margin just in case of any contingencies. If we have to actually release a boulder, go back down and try again, we have some margin in order to do that. And then we have a planetary defense demonstration where we're going to do an enhanced gravity tractor, in which when we actually have the boulder, we are going to demonstrate, we're going to station keep, we're going to thrust our ion engines. So you can see in the diagram, they're canted away, so they're not impinging on the boulder, and that'll be demonstrated for 30 days. And we're actually going to try and impart a delta V that can be measured from the ground. So some of the prototyping and testing that we're doing currently with respect to the robotic vehicle, especially the capture system, you can see here we've got some, this is the landing legs, or the big legs, the CRS, which is the contact and restraint system. This is developed at Langley on an air-bearing floor being tested. We have a microspine gripper, which is going to be the end of two of these robotic arms that is going to actually grip. And they have spines in each one of those little fingers that will hook into the boulder and actually pluck it off the surface. Here's the robotic arm. This is at Goddard. And then here's a mock-up of the actual boulder itself with the robotic arms, and here's the contact restraint systems around it. One of the things I'd like to add that we're excited about is not only are we going to get samples from the boulder, but the landing or the touchdown pads on the contact restraint system will also have supplemental collection capabilities for collecting regolith from each one of those sample pads. So going on to the actual crewed mission segment, basically this is roughly a 25-day mission, a little bit short of 25 days. It's a two-person crew. Again, the launched in Orion, the launch vehicle is the SLS. They're going to rendezvous and dock with the robotic vehicle, and this is in a distant retrograde orbit. It's about 71,000 kilometers around from the moon. They're going to conduct 2 4-hour EVAs, basically have a little break between to rest and also recondition their equipment and their spacesuits, and then have 1 day for contingency and then depart. So here's the trajectory, as you can see. So here's the red line is the outbound. They actually do a lunar gravity assist. So the outbound flight time is about 8 days. The return is very similar. It's in green, another lunar gravity cyst, and that's in 11 days. We have 1 day for rendezvous, and then we have 5 days to conduct our operations. And we think this is achievable within the constraints of the Orion just by itself with a 2-person crew. This is just a diagram to show the EVA feasibility worksite and crew translation in terms of the boulder coverage. So here's the Orion. You'll note there's no airlock, so we have to depressurize the entire cabin. We can do this 3 times, once for each of the 2 EVAs and 1 more for a contingency. The astronauts will translate across the vehicle using handheld and booms, and then they can access any portion of the boulder, and they can also access those pads. So these are the pads I'm talking about here that will have the regolith samples as well. So these are some of the crewed mission kits. So some of the advancements that we've had to do for the crewed mission. Some of this is related to the robotic vehicle. Some of this is related to the Orion. And basically, this is just to demonstrate that we can actually do this mission within the capabilities of the Orion and the SLS. I'm going to wrap up. So with that, I'll take some questions. I refer you to the website here. So if you have any more questions, you'd like to see some videos and some more details, please go to the ARM website. Dan's going to be talking after me. We're both here till the end, so please feel free and come and talk to us if you have any questions. But I'll take questions now if anyone has them. Thank you.
Time for one question.
Hi, big fan of the ARM mission and the science objectives. One quick question though, the characterization of the strength of the boulder, it seems like it might undergo some different kind of accelerations and forces. Has there been thought about it coming apart as you're leaving?
Yeah, so one of the things that we're mindful of is all the things that can happen as you're trying to pick up that boulder off the surface, right? We're modeling that based on the type of material that we think we're going to encounter. We're developing our capture module in order to handle a wide range of strengths and material types. And we're also building in a lot of the contingency modes that we have. So in case we have to let go or do something different in order to extract that boulder, or maybe go to a different boulder entirely, that's where that 50-day extra margin comes into play. Right, so that's what, yeah, good question.
Okay, thanks, Paul.
Yep.